Okay, just one more without numbers. Actually, I'm gonna do another one after this without numbers. Just I wanna do all the like most common forms of loads on a member, right? So shear moment. All right, this time it's a distributed load, and distributed loads are sick. They can do it. You can do all sorts of shit with them. But this is kind of like one of the most basic ones, right? And all it means, the distributed load is just what it sounds like, right? Like force applied consistently along the whole member. Cool. So again, it's just a member fixed to a wall, right? And we got essentially a force. So what's that going to create? A moment, right? And a reactionary force here at the wall at A. So which way is that moment going? This force wants to bend our beam this way, right? All these forces want to bend it that way, upwards. So our moment has got to counteract that. It's got to go that way if we're trying to bend it that way, right? Balance it out. And there's also, put here, A, Y, M, A. Okay. Sweet. So, here we go, right? We're gonna, I'm not gonna do any equations on this. I'm just kind of doing it so you can get the picture of it, and think about it more conceptually like I do. Like I can see something like this and just go, oh, okay, so there's gonna be a reactionary force here, right? And it's gonna be going downwards. Actually, I just drew it like that because I'm just drawing, but looking at it now, it's gonna be going downwards because all the other forces are going upwards and it's at equilibrium. So all these forces going up, that one's going down, and it's the first one we're dealing with. So, right, forces create shear. We're gonna start down here at A, Y. And then, something that's cool about setting it up like this, right, you get your length set up nicely, but you also can see the integrals at play, basically. So if you have a distributed load, you can go integrate it and get this, and you can integrate and get that, right? So this is just a straight value. This is going to be a linear line, right? It's going to be straight up or straight down, and then this is going to be like parabolic, right? It's going to be like an x squared type deal. So we started down here at AY, which would be the sum of all these. It'd be, the force over the distance. So that's the whole thing right there, but it's negative. And then over time, we get more and more of the force until it brought us back up to 0, right? Easy enough. And again, you think of it, distributed load, it's constantly pushing it over the distance. So it's constantly going up back to 0. And then for the moment, so this is positive moment bending, right? Got our little smiley face out. Positive. So the moment here, we're starting with a moment, is going to be positive. It's going to be up there. And again, like I said, we're integrating, right? So this linear line becomes a parabola type of thing. And so we know we're going to end up back at 0 because, again, there's no more moments acting on it. So we're either going to have it like that or like that, right? Because it's parabolic. And those are our two options. So which one is it? Well, the way I like to think of it is here at the start of the shear graph, we're very negative, right? And we're slightly getting less negative as we come back to 0. So then we think about these, right? And it's going to be the slope instead this time. So we're going to start very negative slope, right? Because this was negative, very negative. We're going to have our most negative slope there. which tells me that it's going to be this one. And it just goes out to 0. And we can erase this one because that is not the right one. Sweet. See you in the next one.